right. Okay, so I just checked on my math lab and it looked like you guys, for those of you who were on my math lab, which is the majority of you, you did an awesome job with the homework. I've never had a class get this many people on my math lab this fast and do that much homework that well. So I'm really impressed. And maybe you came in here with the expectation that it would be online, so you're doing the online stuff really well. So I was really pleased to see that. Sometimes it's like the third week and I've got like a bunch of people with zeros on their homework because they haven't even done anything and haven't even gotten on there. So you guys are off to a really great start. Did anybody have any specific questions on the homework? Okay. If you want to turn your cameras on, I can't make you do it, but I would love to see your faces.
When I logged into the my math lab, I don't see any homework.
What do you see when you go there?
It's just blank for the homework tab.
Really? Because it seems, I mean, everybody else was getting their homework done. Wait, who was saying this? Sorry, I was looking at something else.
Nancy.
Nancy. Let's look at it after class, and maybe I think you can share your screen with me after and show me what you're seeing. But let's look at it after class, okay? Now, Nancy, your name is in here differently. Do you want to be called something else?
No, Nancy's fine.
Nancy's fine. Okay. Just making sure. Okay. Well, if there aren't any questions on the homework, then we can continue solving quadratic equations. All right. Well, let's do that then. I'm going to share my screen. Okay. Wonderful. Were you guys super bummed that there was no quiz today? I don't know. Some people maybe like to just get that first one over with. Yeah, I was all stressed out, like making sure that it was all working correctly in D2L, and I was like testing it and going through all the settings, making sure it would display at the right time, and then I realized like, this is not going to happen today. Oh well. Okay, so last time we talked about solving quadratic equations, and we have discussed two methods so far. I'll remind you. The first method that we talked about was using the square root property. So we said that to use the square root property, we needed to be in a form such that one side of the equation was a quantity being squared, and the other side of the equation was a constant. And as long as you have that form or something that can easily be put into that form, then you should use the square root property. The square root property says that you can just take the square root of both sides of the equation, remembering to put that plus or minus on the right-hand side to get the solutions. So we did a couple of those. We talked about what happens anytime you take the square root of a negative number. I is equal to the square root of -1. So you guys should have had to use that several times on your homework. So we went ahead and we replaced the square root of -1 with I, and then we simplified. We also talked about how in my math lab, and because your text calls for this, we don't usually say the solution is x equals blah, blah, blah. I'm fine with that on a test. Just make sure that in my math lab, you're using this set notation. So the braces will already be there. You're just filling them in. So we did that. Then we talked about how to complete the square, which is something that you learned in a previous algebra class, but it's something that gets forgotten because you don't use it all the time. So we took a binomial and turned it into a perfect square trinomial by taking half of the coefficient of x, which is represented by b over 2 in this case, and squaring it. And then when we did that, we were able to then factor this quantity into the square of a binomial. We used that down here. We talked about creating a perfect square trinomial and then factoring it. We also did that here for number 5. So we took half of the coefficient of x, which in this case was half of 4/9, which was 2/9, squared it to get 4/81, added that to the expression, and then factored it. Now to factor it, we're always taking the variable to the first power, keeping the sign that's behind it, and then half of the middle term's coefficient. And then that whole quantity is squared. Remember, you can always FOIL it out to check to verify that that's correct. Now, all of this was so that we could learn how to solve equations by completing the square, which we did for 6 and 7. Now, we did 6 and 7. Today, I'm going to finish completing the square with number 8. I just want to remind you of how we did this because it has been 5 days. Maybe some of you guys did all of this homework already last Wednesday, and now it's completely like something that I need to refresh your memories on. So for number 6, we knew that we were in the form for solving by completing the square because we had the constant on the right-hand side. Remember, the whole point of solving by completing the square is so that we can get this into a form that looks like we're going to use the square root property. So that means you want the constant on one side and you want the variables on the other side. We took half of the middle term's coefficient and squared it to get 16. It's an equation. What you do to one side, you have to do to both sides. We factored the left-hand side and simplified the right. Now we have a situation where we can use the square root property. Some quantity squared equals a constant. And then we just went ahead and solved using the square root property. We said we always want to have exact answers. That means no decimal approximations. All right, same idea here for number 7. We just moved the constant to the right. And then at that point, we could get this into a situation where we could complete the square. Any questions before we begin, having seen this again? Okay. Wonderful. All right, so number 8. I didn't want to get into this one last time because 8 is a little bit different. I know it looks pretty similar. The big reason why number 8 is different is because in this case, you have a coefficient of x squared that's something other than 1. In the last 2 examples, if we can compare and contrast, in number 6 and 7, in number 6, for example, you just had x squared. And in number 7, you had x squared. In number 8, you have 5x squared. You can't have a coefficient on x squared that's more than 1, or anything other than 1, I should say. So we're going to have to figure out how to eliminate that. And remember, we also want to have that constant on the right-hand side. So we have 2 things to do here. It does not matter which one you do first. So I'm going to go ahead and add the constant to both sides so I can move it to the right. So now on the left-hand side, we have 5x squared minus 2x. And then that constant now shows up on the right-hand side as being positive 2. All right, so the big thing we have to do here is we need the coefficient of x squared to be 1. It is not 1. The only way to force it to become 1 is to divide each term by 5, which is the coefficient of x squared that we currently have. So I'm going to divide each term by 5. Now, remember, terms are quantities that you add and subtract. So I actually have 1, 2, 3 terms here. All 3 of those need to get divided by 5. So I'm going to divide by 5 in all 3 places. Now, I realize that this complicates your life a little bit because now you have fractions that you're dealing with. Such is life. Your new equation is x squared minus 2/5 x equals 2/5. Now, if you have a TI calculator, you don't even have to really do that much by hand with these fractions. If you're good with fractions, awesome. Right now, we're going to go ahead and work on the process of completing the square. Does anyone have a question before I continue? Okay. Again, I'm really appreciating the visual feedback I'm getting from you all. It's really helpful. All right, I'm going to take half of the middle term's coefficient, and even though, yeah, technically the middle term's coefficient is -2/5, it does not matter because we're going to square it anyway, and if you square a negative quantity, it's going to come out positive. So we're going to take half of the coefficient of x. You can think about it as dividing by 2 or multiplying by 1/2. Cancel the 2's and you get 1/5. And then we're going to take 1/5 and square it. Remember, when you're squaring a quantity, you're multiplying it by itself. So 1/5 squared is 1/5 times 1/5, which is 1/25, not 1/10. Be careful. You don't want to lose points on something really small like that. That's going to screw up the whole rest of your problem. Now, this is the quantity that we're going to add to both sides. So the equation that I had was x squared minus 2/5 x equals 2/5. I'm going to take this equation and alter it by adding this quantity of 1/25 to both sides. So now I'm going to have x squared minus 2/5 x plus 1/25 equals 2/5 plus 1/25. And then we'll simplify. On the left-hand side, we're going to factor. We have a perfect square trinomial. We know that because we made it a perfect square trinomial. To factor the left-hand side, we're going to keep the variable to the first power. We're going to keep the sign that's behind the variable. And then we're going to take half of the middle term's coefficient, which was this number, not the squared value, just half of the middle term's coefficient. And then we're going to square the left-hand side to complete the factoring. Now, if you want to do the fractions by hand, that's fine. Get a common denominator and add them up. If you don't want to do that, or you don't just feel like, yeah, I'm okay with that, but not like super comfortable, that's fine. I'll show you how to do it in your calculator if you don't already know. You're taking 2/5 plus 1/25. Your calculator might look slightly different than my display, depending on how new or old it is. Remember that your calculator will automatically do order of operations. So it knows that it needs to divide here and divide here before it adds. So you don't actually have to use parentheses in this case. When you hit enter, you're going to get a decimal. To change that to a fraction, hit the math button and then enter. Enter will give you the simplified fraction. And that will work on any TI 83, 84 calculator. So you get 11/25. For something like that, I don't expect you to show me your work, how you added those fractions. That's not the skill that I'm going to be assessing in this class. I would love for you to know how to work with fractions, but that's not the main goal here. Before we continue solving the equation, any questions here? Okay. All right, now we can use the square root property. We're going to take the square root on both sides of the equation. On the left-hand side, that leaves us with x minus 1/5 On the right-hand side, we're gonna be super careful here. Don't forget your plus or minus sign. And when you take the square root of a fraction, you're taking the square root of the numerator over the square root of the denominator. Now the square root of 11 can't be simplified, so you're gonna have to leave that as the square root of 11. The square root of 25 can be simplified to 5. Make sure that your radical does not look like it's covering the denominator and it doesn't look like the whole fraction's inside of it. Lots of little tricky things going on here. And then to continue solving, you'll have x equals, add 1/5 to both sides. You'll have 1/5 plus or minus the square root of 11 over 5. This is the answer with 2 explicit terms. You can also combine these just to make it 1 plus or minus the square root of 11 over 5, whichever you prefer. They're the same. They mean the same thing. One thing I was going to mention here is we got kind of lucky because of the fact that the denominator here was a perfect square. We could take the square root of 25 and get an integer. The only time you would run into trouble is if that is not the case. You don't want to end up with a radical in your final answer. I don't know if that's going to happen on the homework. I can't tell by looking at it. So maybe I should remind you quickly of how to rationalize the denominator. I'm going to turn my sheet over real quick so that I can just do a quick reminder for you. In college algebra and in trig, you're going to have to simplify your answers because that's what your text author wants you to do. That even includes anything that you would turn into me for a test. So let's say your answer came out to be, I don't know, something like, let's see, I'm gonna switch this just so that I have a good example. Let's say it looked like this. So I'm going to say, what if I had x minus 5, quantity squared, and then instead of having it equal 11/25, let's say it was equal to 11/24. That's a very, very different problem, and it looks very similar. I want to make sure everything else is the same. Yes. So this is like a, what if this happened instead? Well, I'm going to show you what to do if you have something like that come up. Before I do this, does anyone have a question? All right. If you were to get something like this, you're still going to use the square root property. When you take the square root on the left-hand side, you get x minus 1/5. No change there. On the right-hand side, you have plus or minus. Now, technically, yes, you can take the square root of the whole fraction. But you have to remember then that that technically means you have a radical in the denominator. I'm going to show it like that, and then I'm going to switch it out. So yes, technically you have this. You would then rewrite that as plus or minus the square root of 11 over the square root of 24. Now, a couple of things are happening here. One of those things is that the square root of 24 contains a perfect square factor. So you're going to have to simplify that. But the big problem here is that now you have a radical in the denominator. So let's simplify this down a little bit first, and then we'll work on isolating x. The left-hand side is going to stay just as it is. Simplify the radical first before you rationalize the denominator. Remember we talked last time about how to simplify a radical. We said we were going to split it up so that it was the product of two radicals where one of them was a perfect square. So don't use 8 and 3. Don't use 12 and 2. You're going to use 6 and 4 because 4 is a perfect square. So we know the square root of 24 is, we'll take the square root of 4, which is 2, and then the square root of 6 can't be simplified. Yeah, technically you could put the 2 behind the radical, but it looks better this way. So now I'm going to rewrite this denominator as twice the square root of 6. Have I lost anybody yet? We hanging in there, doing okay? Okay. Okay. So what we're going to do now is rationalize the denominator. That means that you cannot leave a radical in the denominator. It's not considered simplified. I'm going to leave the left-hand side by itself. On the right-hand side, I'm going to take my current expression, and in order to rationalize, I'm going to multiply by the square root of 6 over the square root of 6. Now, if it's been a while since you've done this, that's fine. This should all come back to you pretty quickly. That's just why I wanted to remind you of how to do this right now. So you're always going to take whatever that radical is in the denominator and multiply by 1, which is just that radical over itself. Now, don't cancel out these square root of 6's or you've undone the work that you just did. So you'll have plus or minus. Now you have, if you want to go ahead and multiply in the numerator, this is technically the square root of 66 in the numerator. And in the denominator, the square root of 6 times the square root of 6 is the square root of 36. Now, some of you guys might jump already to, wait a second, isn't the square root of 6 times the square root of 6, 6? Yeah, we're going to use that fact in a minute. So it kind of depends on the way that you want to write this. All right, so left-hand side is still there. I have plus or minus square root of 66 divided by, now simplify this radical in the denominator. The whole point is you don't want any radicals in the denominator. The square root of 36 is 6. And now you're just about done. So much of this problem is about the algebra that you learned in your previous class, not so much about solving the actual quadratic equation. So we have plus or minus the square root of 66 over 2 times 6 is 12. And then the last thing you need to do here is just add that 1/5 to both sides of the equation. Now this one I would definitely leave as 2 terms, otherwise you're going to have to get a common denominator and put those together again, which you can do if you'd like, but you certainly don't have to. It's just creating more work for yourself. I'm going to have to remember to, when I put these notes up, to scan this side, but anyway, questions on rationalizing the denominator? Okay. All right, so you might get lucky and have to do one of those tonight, but hopefully you'll be able to refer back to your wonderful notes that you took, and you'll be able to do really well. Okay, that was the last one I had for completing the square. Now we're going to talk about using the quadratic formula, which is probably something that you guys remember pretty well from your previous algebra class. Usually completing the square you learn, and it's kind of in one ear and out the other. What people really like about the quadratic formula is it's just a formula. As long as you remember the formula, you just plug in the numbers. It works all the time. It's not like factoring where it only works some of the time. It'll always work. You just have to remember to put everything in the formula properly. And I know this kind of looks a little bit funny on the notes, so I'm going to rewrite it one more time. Sometimes the formulas come out funny and I don't catch it. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So this formula is going to give you the two solutions to the quadratic equation. Now, there will be instances to any quadratic equation where you just have one solution. I mean, imagine if you were saying plus or minus 0. Well, you're not adding or subtracting any quantity in the numerator, so you would just get one solution. We'll talk about what that means graphically on another day. But the solutions of a quadratic equation in the general form ax squared plus bx plus c equals 0, as long as a, b, and c are real numbers, is given by this formula, which everyone has seen before. So we are going to use the quadratic formula now. The biggest thing here is making sure that the equation that you have is already in the general form ax squared plus bx plus c. If it's not, you're going to have to put it into that form. In this case, the coefficient of x squared is 1. So we would say that a equals 1. The coefficient of x is b, which is 6. Now, because you have a minus sign here in front of the constant, we would say that the coefficient of c is actually negative 16. So be careful with that. Whatever sign is in front of that coefficient, you're going to keep that sign when you label your parts A, B, and C. Okay. Now we're going to plug it all into the formula. To get these solutions, we're going to take negative b. B is 6, so we're going to take negative 6 plus or minus the square root of b squared. Now b is positive. I always put parentheses around b. When it's positive, they aren't necessary, but I try to do the same thing every time just so it's really clear. All right, so b squared minus 4 times a times c. That whole quantity is getting divided by 2 times a. So remember, this term is also in the numerator of this fraction. Sometimes students don't draw their fraction bar out far enough, or their division symbol, however you want to think of it. And it is up to you how you want to simplify this. I am very meticulous with my intermediate algebra students. I have a little bit more faith in you guys being able to simplify this properly. If you'd like, you can do these last products first. It's kind of up to you. So we're just going to kind of simplify this in 2 or 3 steps. So keep this first term the same. Then we have plus or minus the square root of 6 squared is 36. Now, normally I count my minus signs. If you have an even number of minus signs, then you're going to have a plus. If you have an odd number of minus signs or negative signs, then you're going to have a minus. But since I have a negative times a negative, this is going to become a positive. And then 4 times 16 is 64. I guess I didn't need that much space here. And then divided by 2. And again, feel free to also use the chat if you wanted to pop up with a question, but you didn't feel comfortable popping up with a question, you can always type it into the chat. All right, so we have negative 6 plus or minus the square root of 100, all divided by 2. Oh, Sebastian, is that a never mind? Yes, okay. Wonderful. And then simplify. So 100 is a perfect square, so we can take the square root. We have x equals negative 6 plus or minus 10 divided by 2. Now, you cannot leave your answer like this. You're going to get the feedback message that although your answer is equivalent to the correct answer, it is not written in the correct form. You have to simplify this all the way. What that means is you're going to have 2 solutions. One of them is x equals negative 6 plus 10 over 2. And the other one is x equals negative 6 minus 10 over 2. So 1 solution, 2 solutions. Negative 6 plus 10 over 2 is 4 halves. which is 2. And negative 6 minus 10 over 2 is negative 16 over 2, which simplifies to negative 8. So those are your two solutions. Of course, in MyMathLab, that would be a set notation answer where you would have just these two solutions separated by a comma. Any questions on number 9?
I got a question.
All right, go ahead, Ben.
When you did the step where it goes negative 30 or negative 6 plus or minus root 36 plus 64, I did 36 minus 64 because it says 6 squared minus 4 times 1 times negative 16.
So you have to be really careful. That's the most common place that people get stuck on this or something goes wrong is because of this particular simplification right here. If you think about this as being a minus sign, that's fine, but then you have minus 4 times negative 16. So 4 times negative 16 would be negative 64. So you'd have minus negative 64, which comes back to a plus.
All right, that makes sense.
Anyone else? I'm glad you asked, Ben, because like I said, that's the most common place where people would have an error. Okay. Wonderful. We'll do another one. X squared minus 6x plus 25 equals 0. I'll give you guys like 4 minutes to do this one. You see what you come up with. Okay. I'm done with attendance. All right. You should have 3 plus or minus 4i. If you do not have that, I will show you right now how to get that. So we have a equals 1, b equals -6, and c equals 25. Be careful with this one because b is already negative. So when you take negative b, you're taking -6, which is actually +6, plus or minus the square root of b squared. Be very careful here to put parentheses around b before you square it. Reason being, -6 quantity squared is not the same as -6 squared. I'm going to even make a note of that just because it is important. Note. -6 squared is -6 times -6, which is +36. This is one of the most common math errors. There's a whole list of them, but this is a big one. -6 squared. Well, when you do the order of operations on this one, remember that the exponent gets applied before the sign in front. The sign in front acts kind of like multiplying by -1. The exponent comes before the negative. So this is just -36. So it makes a big difference whether or not you include parentheses before you square this quantity. Do the same thing in your calculator. If you enter in your calculator -6 squared with no parentheses, then it's going to pop out as -36. So make sure you enter what you actually wanted to find. Okay, -b plus or minus the square root of b squared minus 4ac, the whole thing divided by twice a. All right, 6 plus or minus the square root of 36 minus 4 times 25 is 100 divided by 2. So in this case, I kept this minus sign that was in front of the 4, and then when I multiply what's behind the minus sign, I'm multiplying 4 times 25. So I get 36 minus 100. Now the quantity under the radical is clearly negative, so that's where you're going to end up getting this I quantity. So you'll have 6 plus or minus 36 minus 100 is -64. So we'll have that under the radical. Now, 64 is a perfect square. However, the negative underneath there is a problem. I'm going to split this up into 2 steps. If you want to do it in 1, that's perfectly acceptable. So I'm going to take the square root of -1 as a separate factor. Remember that I can take 2 numbers and multiply them underneath the radical, and I'll get the same thing as if I were to make 2 radicals out of those 2 factors. So I have 6 plus or minus 8i divided by 2. Now, some of you guys might have gotten all the way here and put a box around your answer. Be careful because this is not simplified. And be careful with how you simplify this. You cannot just simplify between the 8 and the 2 and call it a day, or between the 6 and the 2 and call it a day. If you're going to simplify by dividing out a quantity, you're going to have to make sure that every term is divisible by that number. So notice that the reason we can simplify this is because 2, 6, and 8 all share a common factor of 2. So to divide out that common factor, you could just take every term and divide it by 2. That's normally what I do, or you could show that you're factoring it out and cancel it. I tend to think that students see this better visually when you just say divide every term by 2. So I'm going to do that. So divide each term by 2. So 6 divided by 2 is 3. 8 divided by 2 is 4, and 2 divided by 2 is 1. And when we rewrite this, now we only have a value of 1 in the denominator, so we don't even need to write this as a fraction when we finish this up. We can just write 3 plus or minus 4i. And those are your two solutions. Any questions about using the quadratic formula? Okay. You know what I need to do is set up some sort of, I don't know, like a clicker system. When I was at U of I, we had these things called iClickers, and that's how we knew we could leave our physics class. Once we'd clicked in our 2 quizzes, we'd all leave. It was terrible. I shouldn't be promoting this sort of thing. But we would be given like a question that we had to answer in class, and it would be multiple choice, and then we had to choose on our clickers what the answer was. But then the teacher could see, like, this % of you guys chose the right answer or whatnot. But I'm going to look into this because I know there are some programs that would do something similar. I'd really be interested to see how everyone's doing, because I can't walk around and look at you anymore. I can only just see you on the screen. So I am going to look into that because I think it'd be really useful. All right, last thing in 1.5 is about the discriminant. I'm not going to do number 14 because it's really not a very good problem for this sort of thing. So it's kind of meh, kind of anti on it. So we'll skip it. But let's talk about the discriminant. So the discriminant is a way to determine the number and type of solutions to a quadratic equation. So you're not actually being asked to solve a quadratic equation here. You're just being asked how many solutions will there be and what type of solutions will they be. All right, so the discriminant is the quantity b squared minus 4ac. Now that's the quantity that's underneath your radical in the quadratic formula. The discriminant of the quadratic equation determines the number and type of solutions. If the discriminant is positive, there will be 2 unequal real solutions. So thinking about when you solved the quadratic equation where this occurred, well, for instance, number 9 had this situation. Number 9 had 2, well, where are they? 2 unequal real solutions. In that case, the discriminant was positive. The discriminant was this value under the radical. If you have a situation where the discriminant is 0, then you're going to have 1 real repeated solution. Now imagine something like that could have happened for number 9. If you ended up getting 0 under the radical here, it happens sometimes, then you would be adding or subtracting nothing. And your only answer would have been -6/2. So that would be 1 solution if your discriminant is 0. The last scenario would be if the discriminant is negative, there will be 2 imaginary solutions. And that's something that you saw in number 10. We ended up getting these 2 imaginary solutions. One of them was 3 plus 4i, the other was 3 minus 4i. And the reason we got 2 imaginary solutions is because the value of your discriminant was negative. When you take the square root of a negative number, you're going to get an imaginary number to pop out. So for 11, 12, and 13, we're going to compute the discriminant and determine the number and type of solutions for the given equation. So you're not being asked to solve the equation. You're just being asked, what is the discriminant and what does that tell you about the type of solutions to your quadratic equation? So for number 11, you're again going to go ahead and list out the different components here. A is 1, B is 7, and C is 6. Making sure this is already in standard form, meaning that you need to have 0 on the right-hand side or left-hand side, it doesn't matter. So your discriminant is b squared minus 4ac. B squared is 7 squared. Technically, 7 doesn't need parentheses because it's a positive quantity, but I think it's a good habit to get into when you square a value. Minus 4ac. Remember, you're going to apply the order of operations here. So 7 squared is 49. Make sure that you're multiplying before you subtract. So you're not saying minus 4 times 6. You're saying minus 4 times 6. Be careful of your order of operations. And then you get 25. 25 is greater than 0. That means that you're going to have 2 unequal real solutions. So on MyMathLab, when you do your homework, you're going to have a box asking what is the value of the discriminant. And for that, you're going to enter something like 25. And then the other option will be to talk about how many solutions there are to the quadratic equation and what type they are. So you'll probably have like 3 different options there saying with these 3 possibilities in there. So we're going to say that we have 2 unequal real solutions. Now, 12 is one of those special cases. If you don't recognize it just by looking at it, you haven't seen these in a while, so I would totally understand that. But if you went ahead and labeled everything, as we always do to start out, and you set out to find the discriminant, which is b squared minus 4ac, you end up with 2 squared minus 4, which gives you 0. That's because x squared plus 2x plus 1 is a perfect square trinomial. Half of the middle term's coefficient is 1. Square it, and you get 1. That means that you could even rewrite this as x plus 1 quantity squared equals 0. And because that's the case, you would only get 1 solution to this quadratic equation. The discriminant is 0. When the discriminant is 0, you have 1 real repeated solution. Now, you can probably guess what is going to happen with 13. Before we do that, does anyone have a question so far about the discriminant? Okay. Wonderful. So for 13, I am not going to just say that A is 6, B is -8, and C is -7. Can't do that because I don't have 0 on one side of the equation. It does not matter which side of the equation it is, but you need to make sure that you are in standard form, or I guess your book calls this general form, in order to figure out what these values are. Sorry, that's not on this page. It was on the other page. So make sure that you have all of your terms on one side of the equation. To do that, add 8x on both sides and add 7 on both sides. Change the side, change the sign. Now you can go ahead and label those parts, and this is going to change everything. If you forget to have this equation set equal to 0, your answer will come out very differently than it would have otherwise. So we'll have A equals 6, B equals +8, and C equals +7. And we'll find the discriminant, b squared minus 4ac. And we'll simplify using the order of operations. 4 times 6 times 7 is 168. Now, you're probably going to be asked for the value. On a test, I would probably just ask you to tell me the number and type. And as long as you know it's less than 0, that's all I would really ask you to find. In this case, you would just say the value is -104, which means that you have 2 imaginary solutions. And that's how you use the discriminant to talk about the number and type of solutions. And like I said, we're going to skip 14. It's really not a very good quadratic equation problem. It's more of like a Pythagorean theorem kind of a problem. Oh, sorry. Yes. Is that better, Shannon? Yes. Excellent. Any questions? Okay. So my son is doing e-learning for kindergarten, and it's a total disaster, by the way. But I keep telling him that like he needs to like give this visual feedback to his teacher. But the thing is, these 5-year-olds, they always want to give this positive feedback. So the teacher will be like, all right, everybody, thumbs up if you can see the picture on the page. And like she's having technical difficulties and it doesn't show up. But all the kids are still like giving all these thumbs ups. And I'm like, no, like you can't see it. How are they teaching kids how to read on e-learning? Nah, I don't know. I'm really lucky because my son already reads. But if he didn't, I'd be concerned. I don't know. It's only been the second day of school today, so we'll see how it goes. Mostly they're just learning the technology right now and like meeting each other, which is also, I don't know, show dog. No, he's the dog. No, he doesn't come upstairs. Our dog doesn't come upstairs, so we cannot show dog. Someone was babysitting him once and he got outside and he got all muddy and she was like, I'm really sorry. I tried to give him a bath, but I couldn't get him up the stairs and he was so heavy. I couldn't carry him. He's like 85 pounds. So yeah. Oh, he's a yellow lab. Yeah, he's a yellow lab. Okay. I find this funny because I'm not actually like conversing with you guys, but I'm seeing all the like funny questions pop up in the chat. So I feel like, oh, pictures of the dog. Oh, I don't know. Stick around for the office hour and I'll show you pictures of the dog and the kids. Yes. Okay. The kids are way cuter than the dog though, but I know not everyone's into kids. All right. Yes, I'm sure. All right. Moving out of chapter 1. I know we didn't do a whole lot in chapter 1. It maybe seems like we did because we spent a lot of time in chapter 1. Now we're moving into chapter 2. The official title of chapter 2 is Functions and Graphs. So we're really going to be analyzing graphs and function notation, meaning we're going to talk a lot about a function's domain and range and finding inputs and output values and reading function values off of a graph. So really definitely an area where it's nice to have guided notes because it's much easier to be able to use the graph that's already on the page versus like, let me copy this graph down that you put on the board. All right, so let's see. Why do I have 2 of these windows open? I know what that is. Okay, I'm still sharing. You guys can still see my notes, right? Okay, you're not just saying yes to like make me happy, right? Okay, good. All right. So 2.1, basics of functions and their graphs. So here's all the stuff we're going to do in 2.1. It seems like a lot, but it's just like, here's how to do this. Here's how to do that. Just a lot of little stuff. And I don't think you guys will have too much of a problem here. First of all, let's talk about what a function actually is. In order to do that, we need to talk about a relation. A relation is any set of ordered pairs. The set of all first components of the ordered pairs is called the domain of the relation. The set of all second components is called the range of the relation. Now, A relation is a very general term for any sort of related data. A function is a little bit more kind of specific. You have to meet certain criteria in order to be a function. So lots of quantities can be relations. In order to be a function, it's a little more specific. So a function is a correspondence from a first set, called the domain, to a second set, called a range, such that each element in the domain corresponds to exactly one element in the range. So most of the time here, we're going to be looking for ways in which our relation violates this rule, so it can't be a function. And if we can't find the violation, then we're going to say that it is a function. And I'm going to remind you of this definition. We're going to come back to it because we're going to look at these in a bunch of different ways. We're going to look at sets of ordered pairs. We're going to look at equations. We're going to look at graphs. You're going to see data in a bunch of different ways to talk about whether or not it represents a function. So the first thing we're going to do is find the domain and range of a relation and determine whether the relation is a function. Now, for number one, you're being given a set of data. In the set of data, you're given 1, 2, 3, 4, 5 ordered pairs. For these ordered pairs, we're going to find the domain, which means we're going to look at the first elements in the set. Now, for us, those would be the x values in the ordered pair. Now, when you write a domain and a range, you keep these braces that denote the set notation. So just as you're seeing set braces on the ends of this current data set, you're going to also offset your domain and range with these braces. Do the best you can. If it's like a squiggly line on your test, that's fine. Just make sure it looks like you're trying to create some sort of set notation. To find the domain of this relation, all we're going to do is list out the x values, or the first components in each set of ordered pairs. Now, officially, we only list each component one time. So even though you're looking and seeing that the first components of the first two set of ordered pairs are both -6, don't list them out both times. You only list each element one time. Make sure you list everything, but if you see the same element repeated, just list it once. Okay, so I have a -6. We also have a 5, a +6, and a -4. And that's it. You don't need parentheses here because we're just pulling out all of these x values. That's the domain. Any questions on the domain? Okay. These should be like the easy test questions for you. These like, is this like, what's the domain? What's the range? Is this thing a function? It's not supposed to be super crazy. So if you're like, wait a second, this seems really straightforward. It is. You're not missing anything. The range is the second set, or I'm sorry, the second element in each set of ordered pairs. So for the range, you're just going to start out listing the y values. So the first one is 5, then -7, -6, -1, and -5. None of those values repeated. Just list them all. So there you have the domain and the range. The next question is it a function? And then you'll have to explain why or why not. What do we think? Is it a function? Thinking back to your definition, a function is a correspondence from a first set to a second set such that each element in the domain corresponds to exactly one element in the range. All right, we're using the chat. Benjamin thinks no. Oh, now we're just going to have to start listing out all of our opinions here. All right, Nancy says no. I agree. You don't all have to list it out in the chat. It's not a function. Does anyone want to, I'm thinking Ben or Nancy or Sebastian, does anyone want to unmute and tell me why you don't think it's a function?
Because
I think
they're
the
not
domain's got 4 numbers.
My bad, sorry.
Oh, that's okay.
You're good. Go ahead.
Let's see. 2 people responding. I'm so happy right now. Ben, was that you? I couldn't tell.
Yeah.
Okay, tell me again.
I think the domain, or it's not a function because the domain has 4 numbers and the range is 5 in it.
Yeah, that's one way of seeing it. The domain has 4 elements. The range has 5. Yes. Nancy, were you going to say something different? Because, yeah, technically that's sufficient. But, Nancy, did you have a different observation?
Yeah. Because the domain doesn't, each domain doesn't have a set of the range. So, like, they don't each have a number. So, I guess in a way, my bad.
I think you mean the opposite. If you switch that around to be the opposite, then yes. What you have here is a situation where you have 2 elements in the domain that don't correspond to exactly one element in the range. -6 in the domain goes to 5, and it also goes to -7. So because of the fact that this value in the domain goes to 2 different values in the range, it can't be a function. Now, one way of seeing this without having to really put much thought into it is if you see any values in the domain repeat. So if you, sorry, I'm like covering this with my, oh no, maybe I just moved this out, sorry. If you see any elements in the domain repeat, then it can't be a function. So the fact that you have -6 in the domain twice, right off the bat, that excludes it from being a function. Now, if you had an element repeat in the range, that would be okay, because you can send an element from the range back to the domain, or more than once, but you can't do it such that you have one element from the domain going to more than one element in the range. So I'm going to try to put this into a nice, concise sentence. So no, because -6 appears twice in the domain. That is enough. As long as you say that, that's good. If you want further explanation, if -6 appears twice in the domain, well, it's going to 2 different elements in the range. So it's not going to exactly one element in the range. So we can say it goes to 2 different range values. And that's not okay. So you cannot have numbers in the domain repeat, but if a number repeats in the range, that's okay. So you will see some of those on your homework that you can practice on. I'm going to really remind you before your test to just go over these again, because sometimes by the time we get to the end of chapter 2, people have forgotten about this thing way back in 2.1. So I'm going to remind you to come back to it. Any questions about identifying a function given a set of ordered pairs? Okay. All right. Sometimes you're going to see a relation show up not as a set of ordered pairs, but it might show up as an equation. If an equation is solved for y, and more than one value of y can be obtained for a given x, then the equation does not define y as a function of x. This is much easier to show in college algebra than it is in intermediate algebra, because you guys know how to solve these equations. So we're going to determine whether the equation defines y as a function of x. To do that, we're going to solve for y. Now we're going to solve for y, and if we get 2 or more than one solution, then we're going to say that it's not a function. But if we just get one solution, then it will be a function. For the first equation, if I want to get y by itself, I'm going to subtract x squared on both sides of the equation. This is going to isolate that variable y. So we have y equals, and you can rewrite this in either order. Remember, you can't combine them. They're not like terms. They're going to have to stay separate. I'll just write them in decreasing order because why not? So we have y equals negative x squared plus 16. Now, what you should be thinking here is, if you put in a value for x, some value goes in for x, it gets squared, it gets multiplied by -1, and then you add 16 to it. There's no way that you're going to get more than one value to pop out of here. It's just going to be whatever x you put in, squared times -1 plus 16, one solution. That is a function. Now, sometimes it's easier to show a non-function in order to understand why that one is a function. So I'm going to do number 3, and then if you have questions still about number 2, ask me. So for number 3, notice that this time your second degree variable switched. For number 2, you had an x squared and y to the first. For number 3, you have x and you have y squared. Right there, that's an indicator. So if you get used to knowing what happens with powers on these variables, then you won't have as much work to do here. If I want to get y by itself, so remember that's what we're doing here. We're going to solve for y. I'm going to start by subtracting x on each side of the equation. So I now have y squared equals negative x plus 4. Or 4 minus x, whichever you prefer. Now, I didn't ask you to solve for y squared. I asked you to solve for y. In order to solve for y, thinking back to our square root property, we're going to have to take the square root on each side of the equation. When you take the square root on both sides, remember that on the right-hand side, you're going to apply a plus or minus. When you do that, you're going to end up on the right-hand side with plus or minus negative x plus 4. Now, because you had y squared and you had to take the square root on both sides, you ended up with this plus or minus sign when you solved for y. Now, what that means is no matter what value of x you choose, I don't know, say, for instance, you choose x equals 1. Then you'd have -1 plus 4, which is 3. And then you'd end up with plus or minus the square root of 3. The plus or minus gives you 2 values for y. So if you let x be 1, you're going to get 2 different values to pop out for y because of the plus or minus sign. That's how you know that this one is not a function. Basically, the big indicator is just this plus or minus sign. The plus or minus sign tells you that you are going to have more than one value of y for each one value of x that you select. Or for almost every x value. Technically, if you let x be 4, then you'd get y equals 0. That's the only case where you'd get one value for y. Okay, any questions on determining whether an equation defines y as a function of x? Okay, and you'll have some of those to practice for your homework also. Just remember, it really kind of depends on what the power is on y. All right, now we're going to evaluate a function. Students really enjoy evaluating functions. All right. If you have not seen function notation in a long time, it is written here for you. This special notation, it's f, and then it looks like there's an x in parentheses. It's read f of x or f at x. We pretty much always say f of x. This represents the value of the function at the number x. So when we evaluate a function, we're going to just look at that function at a specific value of x. So for number 4, you have a function f of x equals negative 5x plus 1, and you're going to evaluate f at negative 3. So if you let x be -3. The question that you're asking is, what is the value of f of x? Sorry, do you hear my dog again? Oh, it's so annoying. You hear him? Oh, I never know what you guys can hear, and I hear it loud and clear, but super annoying. Okay. F of -3. So what we're going to do is we're going to look at this function, and everywhere we see x, we're going to swap it out with -3. And just be careful with your signs here whenever you're evaluating these. So you have -5. That's not changing. And then if you have -5x, that means you're multiplying. So we're going to multiply here by -3, and we're going to add 1. And again, watch your order of operations. You must multiply before you add. So -5 times -3 is +15 plus 1. I might as well leave my left-hand side on here. So f of -3 is 16. And you're done. On my math lab, it'll say f of -3 equals, and you're just going to put whatever the value is there. I'm going to show you something that I saw a long time ago that took me by surprise, and I want to make sure that you don't make the same mistake. I'm going to say here, do not. So what the student did was they got to the end, and I'm like, okay, cool, great, everything's good. What's all this extra work below it? Well, what they did was they tried to solve for f. So they divided both sides of the equation by -3. And then they said, okay, f equals -16/3. Okay. Don't do that. You're not solving for x. I'm sorry, you're not solving for f. You are just getting a value for f of x at -3. Okay? You're not solving an equation, you're just evaluating an expression. Well, that's the whole plus c thing. That's a whole nother topic, Gian. Okay. Questions on evaluating a function? Okay. Because we are now going to do that with a variable expression. We have f of x equals 3x squared minus 3x minus 4. And instead of just evaluating the function at some integer value, we're going to evaluate it at an algebraic expression. Yay. Sounds like he's dying down there. Terrible. Oh, he clearly misses them. All right. When we do this, same idea. Wherever you see x, you're going to swap it out with x minus 1 everywhere. So not just when you see it the first time, but every time. So instead of saying 3x squared, you're going to say 3 times and then x minus 1 quantity squared. See that? So swap out the x with x minus 1. And we're going to do that to every term. So instead of saying minus 3x, we're going to say minus 3 times x minus 1. And then minus 4. Boy, I didn't know you guys were so into dogs in this class. I'm not a dog person, clearly. All right, that's that. I think it's like a character flaw if you don't like dogs, so I feel kind of bad admitting it. All right, any questions on the evaluating so far? Because we have to simplify this. And most of the work is in the simplifying. The big thing right here, I would say, is don't forget your parentheses. You can't just drop it in. Anytime you're dropping a value in, use parentheses. Okay, now, I also want to remind you, note, x minus 1 squared does not equal x squared minus 1 squared. You cannot distribute that squared symbol. You must FOIL it out. You would say that it equals x minus 1 times x minus 1. All right, so that'd be x squared minus x plus 1. So I'm just going to do that work off to the side and pop it into my expression. Do we remember how to FOIL? A little bit of nodding, a little bit of staring, like, what just happened? Okay. Remember when you're FOILing, you're doing first, outside, inside, last. So the first terms are x times x, which gives you x squared. The outside terms are x times 1, or I'm sorry, x times -1, which gives you -x. The inside terms are also x times -1. And then the last terms are -1 times -1, which is +1. And then you combine those middle terms. We're doing a lot of that, so you're going to remember it very quickly. Okay, the 3 is on the outside, x minus 1 quantity squared. Well, we just did it. It's x squared minus 2x plus 1. Let me finish the left-hand side up there. If you want, go ahead and distribute in the second set of parentheses. -3 times x is -3x. -3 times -1 is +3. And then you have that -4 at the end. Now we're going to distribute this 3 into the parentheses for this first product. 3x squared minus 6x plus 3. And then if you can combine anything else here, go ahead. Like, for instance, 3 minus 4 is -1. And then just simplify it one more time. You've got some more like terms here. You don't have another squared term, but you have -6x minus 3x. You can combine those as -9x. And then you have a +3 minus 1, which is a +2. So officially f of x minus 1 is 3x squared minus 9x plus 2. So just a lot of algebra going on there. Lots of little things that could go wrong, so be careful. Any questions on number 5? Okay. Wonderful. Number 6, the total cost in dollars for a certain company to produce X empty jars to be used by a jelly producer is given by the function c of x equals 0.8x plus 40,000. Find c of 50,000, the cost of producing 50,000 jars. This is the same thing we just did with some context. The total cost to produce this is given by c of x. You're just being asked to find c of 50,000. So just plug it in. I know sometimes we see word problems and we automatically think it must be crazy hard, it must be missing something. All you're doing here is just evaluating this expression at 50,000. So you'll have 0.8 times 50,000 plus 40,000. You'll pop that into your calculator. I'm sure you can do that without actually seeing my calculator, but whatever. 0.8 times 50,000 plus 40,000 gives you 80,000. And it is a cost, so pop a dollar symbol on there. You should never have to enter a $sign in MyMathLab. It should already be given to you outside of the box, or sometimes it might say like in dollars or something. You should never have to type a $sign, just as a general rule. Okay, the next thing we're going to do is graph functions by plotting points, which is something that you've probably done a lot before. Maybe it's been a while. We are going to talk about how to do this. Now I'm going to use a table of values to graph by plotting points. We have 2 different functions, and some of you guys probably are super familiar with this, and you can already tell by looking at the functions how these 2 are related. But we're going to graph them and see. When you're graphing by plotting points, I would suggest, I mean, technically this is just a linear equation. It's just going to be a straight line. 2 or 3 points will suffice. Since it's just a line, let's go -2, 0, and +2. You can pick any points you want as long as you get the correct graph. I don't care which points you choose to generate those points. So we're going to pick some points for x, or some values for x, I should say. And then we're going to evaluate f of x, which is -2x. We're going to get a quantity for that. And then we're going to evaluate g of x and get a quantity for that. So let's do f of x first. You know, I used to have with me in class every day, like a whole set of colored pens. And I don't know what I'm sure they're like in my purse or something crazy like that, because now I don't have them and it would be really helpful here. Let me see if I have anything like that. Might be super old. They may or may not work. We'll see. Okay. So for f of x, we're taking -2 times x. So -2 times -2 is +4. And then -2x, -2 times 0 is 0. And then -2 times 2 is -4. Now, if you don't remember, when you're plotting points, you're basically just plotting some ordered pairs. For f of x, we have 3 ordered pairs now. I didn't leave myself enough space. I totally forgot that column, so I'll just write down what they are. So the ordered pairs are -2, 4, 0, 0, and 2, -4. So we're taking the x value and as the first element, and then the y value as the second element. Now, when we plot these points, remember that the first element corresponds to the x-axis, which is this one, the one that runs horizontally across your coordinate grid. So the point -2, 4, we'll start at the origin and go 2 to the left and up 4. Remember that a negative on the x-axis corresponds to going left, and a positive on the y-axis goes up. The point 0, 0 is at the origin, and you know this is a straight line, so the third point is basically just a checkpoint to make sure that you've done your work correctly. 2, -4 is 2 to the right and 4 down. And this should look like a straight line, which it does. Let's see, get yourself a nice straight edge here. And make yourself a line. And you might want to go ahead and label it as f of x. Any questions on f of x? Okay. Then g of x, we'll do something similar. Now, you don't have to do as much work for g of x because g of x is just going to be -2x minus 3. You already found the corresponding values for -2x. So if you subtract 3 from them, you'll get to the values for g of x. So for instance, you can take 4 minus 3 to get 1. 0 minus 3 to get -3, and -4 minus 3 to get to -7. All right, so every value here is, oh, I don't want to give away the answer. All right, let's go ahead and plot these points. So we have a point at -2, 1, 0, -3, and 2, -7. I'm going to plot these in a different color. Hopefully they show up nice with my like 20-year-old pen. -2, 1, 0, -3, and 2, -7. Well, -7 is not really on here. I'm going to have to make it be on here. Kind of. And then I will plot my line g of x. Make it autofocus, yes. All right, there we go. Describe how the graph of G is related to the graph of F. Does anyone want to tell me what they think here? How is the graph of G related to the graph of F?
They're parallel.
They're parallel, yes. You can, thank you. Who said that? I don't even know who said that.
I did. Michael, sorry.
Michael, okay.
Yeah, me.
Sorry, your picture or your little square was underneath my screen. I couldn't see it. All right, thanks, Michael. Yes, they're parallel. You can generate every point on the line G by scooting down the points on the line of F by 3 units. So these are parallel lines. You probably learned in algebra that parallel lines have the same slope. Remember that the slope for a function is just the coefficient of x in the function. So because these both have a coefficient of x of -2, their slopes are -2. So yeah, that's how you would know. We can do the same thing for this absolute value graph in number 8. If you haven't graphed an absolute value in a while, that's okay. An absolute value is a V shape. Oops. V shape. So when you get done graphing these, they should look like V's. If they don't, you've done something wrong. All right, same idea. Go ahead, and this time you're going to need more points though, because these are not just lines. You want them to look like V's. You're going to need both sides of the V. I tend to use 5 points for an absolute value. I use -2, -1, 0, 1, and 2. Now, if you feel like you need more because you can't see the whole V, you might need to plot some more points. But this is a good starting point. So we have f of x equals the absolute value of x. Now, if you don't remember what the absolute value does, the absolute value will make any value positive once it's inside those bars. So whatever is inside the bars will come out as being a positive value. It doesn't change the sign. Sometimes students think that it takes a value and assigns it the opposite sign. Not true. It just makes it positive. So when we're looking at evaluating, I might leave myself a little room here for ordered pairs. When we evaluate the absolute value of x, we're taking the absolute value of -2, -1, 0, 1, and 2. The absolute value of -2 is +2. Absolute value is a distance, so a distance can never be negative. And you're just going to be taking the positive value out for all of these absolute value functions. And you get this set of ordered pairs: -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. If you'd like to plot those now, you can. I'm just going to go ahead and pop those values in for G. The absolute value of x, well, you already found the absolute value of x. Just add 2 to it this time. 2 plus 2 gives you 4. 1 plus 2 is 3. 0 plus 2 is 2. 1 plus 2 is 3. And 2 plus 2 is 4. And you generate another set of ordered pairs. Oh, I wrote that one down wrong. And then you can graph these two also on the same set of axes. I mean, you kind of get the idea because you already did number 7, so you know what you're expecting to happen here. But I I guess I was thinking you guys probably haven't seen an absolute value in a while, so it's a good idea to go over the graph of one. All right, so let's see, -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. There's your V shape. Don't curve it at the bottom. I know we get used to sometimes making these nice curved graphs. An absolute value is supposed to have a sharp point. So when you're making your absolute value graph, make sure you have this sharp point on it. And there's your function f. Now to make g, you're just taking the graph of f and shifting it up 2 units. We're going to talk about this library of functions, and once we get into some of the later sections, it's 2.5. We'll talk about how these graphs are different and how you know what to expect. But for the graph of g, I'm just going to plot these ordered pairs. And you can see now how the two are related. These two functions. All right, we're almost done for today. Almost done. Any questions on 7 and 8? Everyone's getting so dark on the screen. I'm probably getting all dark too. When I turn the light on though, it makes my notes look crazy. As long as the notes look okay, we're good. Okay, use the vertical line test to identify functions. If any vertical line intersects a graph in more than one point, the graph does not define y as a function of x. So we're going to use the vertical line test to determine whether or not the graph is a graph in which y is a function of x. So what we're going to do is we're going to drop some vertical lines down. Our goal is to see if there's any one place on the graph where the vertical line would intersect the graph more than once. Now, when I say the graph, I don't mean the coordinate axes. We're not talking about the y-axis and the x-axis. We're just talking about this parabola itself. So if you started to drop vertical lines down this parabola, you would not be able to find a spot where you would hit the parabola at more than one point. You hit the parabola once in all of these locations. But you would never hit it twice. That's how we can tell that this graph does represent a function, because of the fact that you cannot intersect the graph more than once with any vertical line. I think yes will suffice in this case. Now, there are a lot of non-examples here for sketching a graph that fails the vertical line test. One that comes to mind would be a sideways parabola or a circle. And you can do a quick sketch of one of those just to kind of give you an idea of what that would look like. Now, you haven't done a lot of work with graphs that are not functions in your lives. You've, I guess, talked about circles, and we're going to be talking about circles later on in this class. But let's say you had some circle somewhere on your grid. Now, you can't say, oh, well, if I dropped a vertical line right here at the end point, I would only intersect the circle once. It must be a function. You can't do that. You have to make sure that the opposite is true. You need to find a spot where that is not the case. And that would be any other spot except for this endpoint. If I dropped a vertical line here, well, those are the two places where you would end up saying, wait a second, I dropped a vertical line through and it hit the graph more than once. Therefore, it can't be a function. So you would say not a function. So of course, a vertical line is not a function because you would basically hit an infinite number of points on the way down that vertical line. So something like this, a sideways parabola, occasionally you'll see something that maybe looks like a cubic function. All right, I should be labeling my axes here. Like this. And you might even see it just squiggle a little bit in the middle. This one's a little more obvious. I mean, technically you could drop a vertical line here and you'd be okay. You only cross through once. However, you're looking for a spot that makes this not true, which would be somewhere in here where a vertical line would cross through the graph 3 times. So this would be not a function. Okay. That's the vertical line test. Any question on that? Oh my gosh, my dog. Okay, we're gonna have to call it a night here. We'll finish up. I think there's just one more page. Yeah, we'll finish up this page on 2-1 on Wednesday. Couple of things I wanted to mention real quick that I thought I forgot to mention at the beginning. Remember I had told you guys last time that if you accepted the Google Calendar invite, that you would end up being able to view the video of the class. That's true. You can still do that. I think it takes you to a Google Drive link and you can view it from there. It might be easier for you to see the YouTube link. Would it be? I don't know. I don't know if anyone's watching it, but if you can't come to class one day, you might decide to watch it. I'm going to try to remember to upload these to YouTube. The only thing is I start to upload them and then it sometimes processes really fast and other times it's like 2 hours later and it's still not processed and then I forget about it and then I forget to post the link. So what I did though earlier today was I set up in the content section of D2L something called YouTube video links. So what I'm going to do is I'm just going to post the link for each video so that you can view it on YouTube. If you find that easier, you can still access it from your Google Calendar. I had students last semester who really loved using the calendar feature, and then some of them used the YouTube link. I also think when you go to my YouTube page, you can see any of the videos that I've made of my class. I haven't even taken down the ones from last spring, so those are up there too. But all right, those will be up there, and up until we get to 2.6, I'm going to post these notes. After that, you're going to have to fill out your own guided notes and look at them because that's how I'll know that you're doing what you're supposed to be doing. But the copy shop, I sent them everything. It was a big, huge hassle. There was a lot of confusion, but they are supposed to be sending out notes for you guys from 2.6 all the way through chapter 8, and you should be getting them, I hope in time, but they said they're going to mail them out next week, and that was Friday, so I'm assuming this week. So those should be heading your way. That is all. If you think of anything else you want to ask me, stick around for the office hour. I'll be on until about 7:55. I'll see you Wednesday. I'm going to put some homework up now. The 1.5 stuff should already be available for you. So have a wonderful evening.
Thank you. Bye.
Thank you. Bye-bye.
Thank you.
Thank you.